So we have now Craig Lawrie from DC, who will tell us about generalized symmetry constraints on deformed 4D SCFTs.
Perfect, thank you. I'm sorry if I tripped you up there because you notice the title is very different from the one on the webpage. So if you do want to talk about polarization pairs and relative theories, you can come and talk to me later. Instead, today I will talk about a paper which came out just a few weeks ago where we thought about generalized symmetry constraints on deformed 4D SCFTs. Nicely, Lawrie gave a very similar introductory question, so I will just repeat that again. What are symmetries good for? Well, okay, we know this. What are symmetries good for in 4D gauge theories? And more generally, what are generalized symmetries good for in 4D gauge theories? And this is the question I will try and say something interesting about today. So one of the reasons symmetries are interesting is that symmetries can have anomalies. And anomalies are sort of topological properties. They behave very nicely. So there's a property called Toft anomaly matching. And Toft anomaly matching says that if you have some UV theory, which perhaps is some weakly coupled theory, think about, say, QCD at high energies, and there exists a flow of that theory into some IR. That IR may be some strongly coupled thing with a whole bunch of fun features, confinement, dynamical symmetry breaking, whatever you think of. The anomalies of this thing, which is complicated, must match the anomalies of this thing where everything is weakly coupled and you can do a computation. So one of the things that symmetries buy you is that some complicated theory must have a certain behavior. So let's say that I have a theory up here with an anomaly that I can compute, and I want to know what are the consequences for the theory down here. In general, there are three options. Well, there's one thing which cannot happen. The thing which cannot happen is you have what's called a trivially gapped vacuum down here. And what you can have, you would have a gapless vacuum, basically some CFT, some massless degrees of freedom. You can have a gapped vacuum. In this case, you have topological degrees of freedom. Or you can have some symmetry breaking. But whatever happens, whenever one of these options is realized, it must produce the correct values for the anomalies that we computed up here. Okay, so this is a bit up in the air, so let's be a little bit more concrete. So in 4 dimensions, quantum field theory can have a mixed anomaly between a zero-form symmetry, a regular standard symmetry that we've known for a long time, and a one-form symmetry. So let's look at a couple of examples. If I take pure SUN Yang-Mills theory at theta angle equals pi, and this was a very nice piece of work done by these authors in 2017, we said at theta equals pi, there is a zero-form symmetry, which is just a Z2 corresponding to time reversal symmetry. And there is a one-form symmetry. I'll explain how we determine this in a few minutes, but just take it for now. And there's a mixed anomaly between these two symmetries. So what this means is that one of the things on the previous slide have to happen. And these authors argue very plausibly, that way, that the first two options are actually ruled out by different methods, and that you should be in a spontaneous symmetry breaking phase. You have two options. You could break this Z2, or you could break the Zn. If you break the Zn, then your theory no longer confines. That's also believed not to happen from lattice simulations. And so they conclude that the anomaly tells you, combined with this other evidence in a sort of holistic manner, the anomaly tells you that there's spontaneous symmetry breaking of the Z2 time reversal symmetry, and you end up with two degenerate vacua. So that's nice. We use the anomaly, and we learn something about the IR behavior of this quantum field theory. Again, this is a strongly coupled thing, so anything we can say is great. Here's another example. Take pure n equals 1 Yang-Mills. There's a Z2n zero-form symmetry, that's the axial symmetry. Again, there's a Zn one-form symmetry. And again, you can do a computation and you can see that there's a mixed anomaly between these two symmetries. Okay, what happens in the IR of the system? Well, you have gaugino condensation, we know about from, textbook material nowadays. And what happens is that the gaugino condensation breaks the Z2n axial symmetry, to just a Z2 subgroup, and you have n degenerate vacua. And indeed, if you look at the mixed anomaly between these two things, the only subgroup of the Z2n which does not have a mixed anomaly with the Zn is the Z2 subgroup. Okay, so we're only learning what in this case, we're only learning what we already knew, but it's nice to see that the structure of this new anomaly matches with what we knew. So we would like to have some more examples. Maybe some more examples where we didn't already know the answer. However, if you start with a superconformal field theory, or sorry, if you start with a supersymmetric field theory like this, and you say, well, the obvious thing to do is I add some matter. Typically, when you add the matter, you get something which is an SCFT in the infrared. And maybe an SCFT in the infrared is not so interesting, because if you say, well, it's an SCFT with this mixed anomaly, you're not saying very much. Part of that reason is there's sort of a belief that any anomaly you want, there exists a CFT which can saturate it. Maybe this is not a good folklore belief, but as a motivation, we might say, can we construct some examples where we have a mixed anomaly, like here or here, and we have no infrared SCFT, also like here. And to do this, we'll do some deformation, which is the deformation in the title. So what we do is we start with a supersymmetric gauge theory, where it has a weakly coupled UV where we can compute some anomalies. We assume that that theory, well, determine that those theories flow in the infrared to some superconformal field theory, also with a mixed anomaly. And then we ask, can we do a deformation of that theory, which preserves the mixed anomaly, but breaks, in this case, the R symmetry. If you break the R symmetry, then, modulo a subtlety, you probably do not have superconformal field theory in the infrared. Disclaimer, you could have emergent abelian symmetries and emergent CFT in the infrared, but let's not dwell on this slight disclaimer. So this would be the kind of case that we would be interested in. So it's schematically depicted like this. Start with the gauge theory, flow to a CFT, turn on a superpotential deformation which breaks the U1R, preserves the mixed anomaly, you get something, and then ask questions about what's going on in the infrared of this system. Can you say something about the structure of its vacuum?
What does it mean that it breaks the symmetry? Does it break the
No. It breaks the U1R symmetry. The U1R symmetry is not part of the mixed anomaly.
Okay.
Thank you. Great. Yeah. So first we have to talk about this side of the story, and then look at the deformations. So I phrased this as a series of questions, which we will answer one after the other. So what are the 4D n=1 Lagrangian theories with simply connected simple gauge group that flow in the infrared to an interacting SCFT and with non-trivial one-form symmetry? So I don't have time to dwell on both of these points. So here's a very fast answer for when it's an infrared SCFT. Basically, you have a bunch of matter in some representation. As long as it's asymptotically free or conformal, there exists a well-defined R symmetry, and there exists at least one operator which transforms non-trivially under this R symmetry, so it doesn't decouple. Then you expect an interacting SCFT. This is essentially the collection of conditions which gives you the conformal window for SQCD, stated for general supersymmetric QFT. Instead, I will focus first on asking when there is a non-trivial one-form symmetry. So if you have a simple and simply connected gauge theory with matter in some arbitrary representation of the gauge group, then there exist codimension 2 topological Gukov-Witten operators that are in one-to-one correspondence with elements of the center of the gauge group. So if these topological operators are non-trivial, then they're generators of a one-form symmetry. This is what these gentlemen here taught us in 2014. So the game we need to play is just to ask which of these topological operators are trivial.
It's true without the matrix. The matrix not the set. It's another group.
No, the answer to the question you just asked is what I'm about to say, basically. So there are topological Gukov-Witten operators in the center, as long as the gauge group is simple and simply connected. But if you have matter, a bunch of them will become trivial. And then you get a subgroup of the center as the one-form symmetry. Exactly the statement, some of the Gukov-Witten operators link with Wilson lines. Really? I started late. They are non-trivial only if the linking number is 0, with Wilson lines which end. So you just have to compute which Wilson lines end, and there's a sort of nice, simple formula which just depends on what's called the n-ality of the representations. Okay, so you can just work it out, and this subgroup of the center is the one-form symmetry. Okay, so we run through this game, and these are all the n=1 gauge theories with non-trivial one-form symmetry. There are some infinite series and some sporadics. They're also orthosis and blended, but I don't write them here. Okay, so now we have to move to the second question. What are the theories which also have a mixed anomaly? Because we would like to constrain the IR physics. So we'll focus on SUN with just a ZP one-form symmetry. We turn on a background field for the one-form symmetry, and we perform an axial rotation. The partition function picks up a phase, and the phase looks like this. And what we remember is that in the presence of a background field for the one-form symmetry, the instanton number can be non-integer. If the instanton number is non-integer, this phase is non-trivial. A non-trivial phase of the partition function is exactly what an anomaly is. Okay, so we can just work out what the instanton number is with this combination of things, and you get this number. And so there's a mixed anomaly if this thing is not 0 mod 1. You have to worry about the space-time, but let me not dwell on that, whether you have spin structure or not. And you can do the same analysis for SOSP, and you see that it only depends on the choice of gauge group and the particular one-form symmetry, but it doesn't actually depend on the number of elements inside of the axial symmetry. So we just apply this criteria to all of the theories in the previous tables, and we see which theories have non-trivial mixed anomalies. Okay. So we covered this part of the story, and now we ask the third question. What are the theories that solve question 2 and preserve the anomaly upon supersymmetric deformation? There are many examples. There are a bunch of infinite series. There are some sporadic examples. We explore all these in the paper, so I won't dwell on it. For, say, this example, there are two kinds of deformations, mesonic, baryonic. In this case, you break the U1R, and you have a mixed anomaly, which basically depends on the power here. So these are examples where you can say something about the infrared phase, and it's not a CFT. So let me finish by doing a quick example in a little more detail. Take spin 12 gauge theory with a chiral multiplet in the 77 representation. The symmetric doesn't screen any of the center, so you have a Z2 times Z2 one-form symmetry, and you have a mixed anomaly for axial transformations parameterized by an odd integer. There are a bunch of relevant operators of this SCFT, and the superpotential deformation breaks the Z8, Z28 axial symmetry to these things. The Z2s are generated by L even, so there's no mixed anomaly. But the Z4 is generated by L=7, which is an odd element of Z28, and so there is a mixed anomaly in this case. So, for example, start with this gauge theory, flow to the infrared, do a deformation, not sure why that's there, and then flow into the infrared. What's going on here? So, there is an anomaly. So this theory does not have a trivially gapped vacuum. There's no obvious U1R, which indicates that the theory is not conformal, so it's not a unique gapless vacuum. If you use the analysis of Cordova-Omori, then it tells you that the infrared, basically the anom TFT, cannot be does not exist, is not consistent, and so there is no unique gap vacuum. So the anomaly should be saturated by spontaneous symmetry breaking, and the minimal pattern of spontaneous symmetry breaking is you break the Z4, that's the zero form symmetry, to a Z2, and you have two confining degenerate vacuums. So we've been able to draw some conclusions about, say, this. Okay, quickly looking at the extensions. There was no reason to consider gauging chiral multiplets together. We could gauge superconformal field theories together, sometimes called strongly coupled matter. And you can see you have a much richer spectrum of relevant deformations. You can see things about dualities and start matching these mixed anomalies across dualities. So this is a gauging of two Argyres-Douglas theories, and this is a Lagrangian gauge theory, and you can see that these things flow to the same IRS-CFT, and you could match the anomalies. You can also ask a non-supersymmetric question. This is exactly the same as question 1, except now I don't worry about CFT in the infrared, because I don't know how to answer that question in a non-supersymmetric setting. But we did this as well, and you can, compute the mixed anomaly and rule out, say, unique gap vacua. In fact, you can actually also compute the three-loop data function, and sometimes you see that there looks to be exact type CFTs that could satisfy the mixed anomaly. So the conclusion that I want to say is that the mixed 0-form, 1-form anomaly is just kind of a holistic part of a whole approach to constraining the infrared. You need much more than the anomaly, but it provides a whole bunch of constraints, and a whole bunch of theories can be constrained in this way. All right, so I'm out of time, so thank you. Yeah.
So it is not that for theories that have a 1-form and 0-form mixed anomaly of that type, if you gauge the 1-form symmetry, so you change the global form of the gauge group, then you have a non-invertible, like the 0-form symmetry becomes non-invertible. Do you think you can derive some dynamical consequences for that forms of the gauge group, or?
Yeah, so this is something I would have talked about in the future directions, because this is a great question. So in everything here, I focused on the simply connected gauge group for the reason that, well, for simplicity. So you can choose different polarizations of the defect group. This corresponds to a different choice of 1-form symmetry. You can look at, say, mixed anomalies between magnetic symmetries. You can look at the non-invertible symmetry that you get as a remnant. And you could try and have something to say. And there I think you have something to say with the symmetry TFT. But it's not something we've done yet. But I think you could end up with this kind of phase diagram. The kind of phase diagram you know how to draw very well. And I think you could do the same thing here for all of the different choices of polarizations.
You know the TFT polarization, the other ones is
Exactly. I think you could just, plug it in and draw the picture for all of the different gaugings of the 1-form.
Have you looked into the option of discrete Green-Schwarz terms to kill these anomalies?
Discrete Green-Schwarz terms. You mean in which, like in a symmetry breaking phase, or?
I guess in general, like if your theory contains these, discrete topological terms, like
Yes.
usually, okay, like the local physics is,
Yes.
insensitive to them, and you may not know about them unless you look for them, and maybe the anomaly is affected by these. Is what I'm saying.
Good, thank you. So there were some warnings on one of the slides that I didn't highlight that you have to check for these things to see whether you can cancel the anomaly with them, and we did check. So it's different from the story with the TTT story. So in the TTT story, there are such terms that you can add which cancel the anomalies. And that basically comes in because the Z2 time reversal symmetry introduces a minus sign somewhere, and then you can cancel two terms. Here it's sort of a positive cyclic shift, and so the only time where the counter term would cancel the anomaly is if there isn't one. The computation of that's in.
Thanks.
So can you try to actually spontaneously break the 1-form symmetry?
Indeed, so I glossed over this option by saying if you have confining vacua, then you have spontaneous symmetry breaking of the zero form. You can also imagine breaking the one form symmetry and having some kind of deconfined phase. So that's equally an option for saturating some of the anomalies. So there's some work by various people, Bojan and Clay and so on, who thought about what happens.
So that's also an option.
But that's also an option. I sort of include this in the spontaneous symmetry breaking option.
Okay.
But yeah, I didn't.
And can the U1R be emergent?
So the U1R in principle could be emergent. So I don't want to claim solidly that the fact that you break the U1R like with the deformation in the UV means that you don't have a CFT, because there are situations where some U1R emerges along the flow into the infrared, and then any abelian symmetries, and those can mix with the R symmetry and end up with the CFT. So in that sense, you always have to think of this as providing sort of some constraints. And so if you want to argue it's a CFT with this anomaly and this deformation, you have to sort of make an argument why something emerges. So it's, yeah, constraining the space as opposed to giving an absolute answer for what's going on.
So let's thank Craig Lawrie again.